Hi, so we're going to talk about volumes of revolution. And you might think, well, that sounds familiar. Well, maybe we won't have to talk about it. Let's see if we've already done this before. So we've got this plane region right in here, and we want to revolve it about this axis over here to form a solid of revolution, and we want to be able to find the volume of that. So if you remember from our previous talks, there's two ways we can get solids of revolution. We can do the disk method and the washer method. In both cases, to make disks and washers, you have to have the rectangle perpendicular to the axis. So I would have to make the rectangle on the side. And at first thought, that's not a problem. But what you have to remember is if your rectangle is on the side, all your measurements have to be done in terms of the x distance. So if this function is y is a function of x, then we have to turn it into x is some function of y so that we can make all those measurements to get the radii in our formula. And that can happen a lot of times. If this was y equals 2x, you could get x equals 1/2 y. If this was y equals x cubed, you could get x equals y to the 1/3. But you can't always solve for x in terms of y. That is the problem, and that's what we're trying to deal with today. So if you can't solve for x in terms of y, we have no choice but to make our rectangle up and down like this. So I'll kind of go through this fairly quickly because we've done it so many times. We would divide from A to B up into a lot of different sections, like n of them. And this will be the kth section from xk minus 1 to x sub k. And then somewhere in between we pick a value of c sub k. And that becomes the height of our rectangle here. Now the question is, when we revolve this rectangle this way, it's not going to make a disk or a washer. Is it going to make something that we can geometrically find the volume of? Because if it doesn't, this isn't going to do us any good. So think about what this figure is going to look like if I take that rectangle and revolve it around here. Remember, the width is delta x sub k. So you have this little bit of width that you're revolving around this axis. So the height of this object is going to be the same as this. You're revolving it around, so the radius is going to be about that big, but then when you revolve it around, it's going to look something like that, except you've got a little bit of width. So it's forming like a cylinder, but we're not really getting the volume of what's inside of the cylinder. It's going to be this thin outer layer, and then it goes a little bit of thickness inside there. So it's this little, what we call a shell. So it's a cylinder with a really thin shell. So it has some thickness, but not very much. Now, can we get the volume that would be in this shell? Well, what we want to do is take the circumference, and the circumference is going to be 2 pi r, and then multiply that times the height, h, and then that will give us the surface area, and then if we multiply the surface area times this width, we're going to get the volume. So whatever that width happens to be. So this is the geometric formula we'd have to do to get the volume of this shell, as we're calling this. Well, let's see. 2 pi is just a constant. R is this radius right here, so that would be coming from here to here. And you can see that that's a function of where I pick this c sub k. If I had picked the rectangle over here, it would be a bigger radius. So this is not a constant, it's a function of where I pick c sub k. And then how about the height? The height is also a function of c sub k. And what's the width? The width is just this delta x sub k that we've had in a lot of our other forms that we've done. So this is going to be the volume of this one shell. Well, then we're going to have to add up all the shells from k equals 1 to n. And as always, we're going to have this little bit of error in here. So we take the limit as n approaches infinity. And then the shell becomes so thin that we don't have to worry about the radii being different on the inside and the outside. And what we've got is an infinite Riemann sum. This is a function of x, this is a function of x, and in our definite integral, that's going to be our dx. So to find the volume, we've got a formula. It's the integral from a to b of 2 pi, and we could bring that 2 pi right out front, and then this is going to be r of x, h of x. And that is the formula for shells. That finds the volume of a solid of revolution using the shell method rather than the disk method or the washer. And how are you going to know when to use it? It's when your rectangle is parallel to the axis and not perpendicular. So let's try a couple of examples and see if this works. Find the volume of the solid of revolution when the region bounded by x equals 0, y equals 0, so the x and y axis, x equals 1, and y equals 3 plus the square root of x. So it starts out at 3, and then you go plus the square root of x. So by the time you get to 1, it's going to be up to 4. And it's going to keep going out like that, but this is the area right here, and we're revolving that about the y-axis. Now, which method should we use? Well, we have y as a function of x, so we can make our rectangles up and down, but we could solve this for x. Algebraically, I could solve that for x. So this one we could do either way. But I think there's some advantages to go up and down. If you made your rectangle sideways, you'd have a different rectangle here than you would over here. This rectangle would be going from the curve to the vertical line. This would be going from the y-axis to the vertical line. So you'd have to set this up in 2 integrals, plus you have to go through the algebra of solving that. So I think in this case, we're not required to do shells, but I think it's going to be to our advantage. So that's going to be dx, and then we can write our formula. The integral from, what do we have in our formula? We have 2 things we need. 2 pi always is there. That's just part of the formula. Then we need 2 separate functions of x, and then dx. Well, the height is not found any different than we've done before. The height is right there. And what is that distance from the x-axis up to the curve? That's the y value on the curve, or 3 plus the square root of x. Now this is where it gets a little bit different. What's r of x? Well, r of x is the radius of this shell that you're revolving around. Well, we're integrating from x equals 0 to x equals 1. And notice, wherever you happen to be, that's what the radius is. So when x is 0, this rectangle would be right up against the axis. When it gets to right in the middle there, the radius would be 1/2. So when x is 1/2, in our integration, that's what the radius would be. And the same thing when you get the rectangle out to this far side, then the radius would be 1. So the radius is whatever x happens to be. It's a function of x. It happens to just be x. So then we have our setup. So then the next step would probably be to multiply this through. So you get 3x plus x to the 3/2. So now I can take my antiderivative of 3x would be 3x squared over 2. And for x to the 3/2, it would be x to the 5/2 divided by 5/2, or times 2/5. Again, 0 is going to give us 0. 1 is going to give us 3/2 plus 2/5. So the common denominator is 10. You get 15 plus 4, or 19/10. So if you multiply by the cube pi, you get 19/5 pi. And that would be the number of cubic units of the volume of this solid of revolution when you revolve this around the y-axis. So easier to do by shells, but we could have done it by discs. Because if we had made our rectangle on the side, it would have been right up against the axis. So let's do another one over here, where I have y as a function of x, and I cannot solve for x as a function of y. Therefore, no matter what I'm doing, I have to make my rectangles up and down, vertical. So let's see what this one turns out to be. The region bounded by x equals 1, y equals 1, and y equals x cubed plus x plus 1. So when x is 1, y is 3. When x is 0, y is 1. So we get something that looks like that. And this is the region right here, and we're going to revolve it around x equals 2. So there's our axis. So we do have space in there, so if we had our rectangles on the side, it would be washers. But we really don't have a choice this time. We have to make our rectangle up and down, because I can only solve this for y. So right away, since the rectangle is parallel to the axis, I'm going to do shells. And with shells, you always have two things you need. You need the height of the shell, and you need the radius. So the height is this y value, which is x cubed plus x plus 1. Didn't leave myself quite enough. Minus this y value, which is 1. So you get x cubed plus x plus 1 minus 1. So turns out to be just x cubed plus x. What is the radius? The radius is from the rectangle to your axis. And what do we know? The distance from the y-axis over, like we found here, is called x. Whatever the x value happened to be. So what is this going to be? That's going to be 2 minus x. Because this whole distance is 2, and from the y-axis over to this is x, so this is going to be 2 minus x. So it'd be just a matter of multiplying that out. Oh, and you're going from where? You're adding them up from x equals 0 to x equals 1. That's where those rectangles would go. So it wouldn't be too hard to do. I don't want to spend too much of your time on doing the fundamental theorem, multiplying things out. The answer turns out to be 29 pi over 15. If you want to give it a try yourself. But anyway, the important thing is how to set it up. We had to do this one with shells, and then how we find the height is the way we've always found it before. This y value minus this y value. The thing that's kind of new is the radius. But as long as you know that the distance from y-axis over to here is always going to be x, then we can always find the other as a function of that. So let's go over to the other board and do another one that's slightly different. This time we have a solid of revolution formed by taking a region in the first quadrant bounded by this sideways parabola and the y-axis. So when y is 0, x is 0, and when y is 1, x is 0. And when y is between 0 and 1, this is positive. So it's a parabola that comes like this and goes like this. But we're only really concerned in the first quadrant. And there's the y-axis. So this is the region. It's not a very big region, but we're going to revolve that about y equals 3 up here. Now here's one that is solved for x, and we can't solve it for y. There's no way we can algebraically solve this for just y in terms of x. So we have no choice but to make our rectangle on the side. So that's going to be dy. Now, I think I've done it enough times with other methods that you can see it's going to be the same thing in dy as it was in dx. The only difference is the volume is going to be 2 pi. You still need those two things, but it's going to be dy instead of dx. You would just be dividing it up in the y direction. And I think you agree that we have to do shells because this rectangle is on the side. It's just like y equals 3. They're both horizontal. They're parallel to each other. Therefore, we have to use shells. And y goes from where? You're adding them up from 0 to 1. Now, what are the two things we need? We need the height of the shell, which it's on their side this time, but that's going to be the height. And that's the x-coordinate on this graph. So that's just y minus y squared. And then, what's the radius? Okay, so this is a little bit different, but the radius would be that vertical distance there. Well, what do we call the distance up from the x-axis? We would call this distance from here to here y. The distance up from the x-axis we always call y. So this is y. So this purple distance right here is going to be 3 minus y. And that's going to go as our radius. And just like the other one, you'd have to multiply that through, take the antiderivatives, and plug in to get your answer. Instead of actually doing that, let's say if we took that same region and revolved it around y equals -1, down here. Well, it's still parallel. It's still got to be shells. So I can basically just write the same thing. The only difference is the radius changes. Actually, this height doesn't really change. It's going to be the same as it was before. So this is exactly the same setup, except this changes. Well, what is that distance going to be now? Now you're from here to here. You're revolving it around like this. So we know that this distance is 1, and that is y. So it would just be y minus a -1, or just y plus 1. And you'd get a different answer than this. It would make a different figure. But again, it's very similar to this one. So that's one in the other direction. So let's just kind of finish off with one here that we could end up doing in both directions, but let's see if there's one way that looks better than the other. So we have x equals 1 and y equals 1 as boundaries. And we have y equals 8 as a boundary. And then y equals 1 over x cubed. So when x is 1, y is 1. And when x is 2, y is 1/8. So you're down here. So you have something that looks like this. And this is the region that we're going to revolve it. And where are we going to revolve it about? X equals 4. Now, we can solve this for x. But I'm thinking, if we solve it for x, we have to have the rectangles on the side. And the top rectangle would be between these two vertical lines, but when you get down here, it's going to be between this curve in here. So we'd have to do two separate integrals. So this one we do have a choice, but I'm going to prefer to make one rectangle and not to have to resolve this in terms of x. So that means this is dx. And right away we can say, since it's parallel to the axis, we're going to do shells. And where are you going to add them up from? From x equals 1 to x equals 2. We always need two things. And how do I get them? Well, the height of the shell is going to be from this y value to this y value. So it would be 8 minus 1 over x cubed. And the radius is going to be like this. So from here to here is x, and then this is going to be 4 minus x. just to convince you about the radii, let's try it. When you start out your integral at x equals 1, what's the radius going to be? 4 minus 1 is 3. So does that make sense? When you have your first rectangle right over here, the radius is from 1 to 4, so it would be 3. By the time you get to x equals 2, the radius is going to be 4 minus 2, or 2. By the time you get your rectangle over here, the radius would only be 2. So I'm hoping this idea of finding the radius is making sense. Well, let's just finish out this one. It's a little bit harder. 8 times 4 is 32. And then you have minus 4 over x cubed. And then you have minus 8x. And then plus 1 over x squared. If we're going to have to do an antiderivative, I want to probably put these in negative exponents. So what's the antiderivative of 32? 32x minus 4. This becomes x to the negative 2 divided by negative 2. This becomes minus 4x squared. And this becomes plus x to the negative 1 divided by negative 1. Well, let's just write this a little nicer. 32x plus 2 over x squared minus 4x squared minus 1 over x. And we're going from 1 to 2, and we still have the 2 pi out front. So if we plug it in, we get 64 plus 1/2 minus 16 minus 1/2. So the 1/2s cancel out. When we put in 1, we get 32 plus 2 minus 4 minus 1. So altogether, 48 minus, and this is 29. So we get 19 times the 2 pi, or 38 pi. And that would be the volume. So anyway, just to conclude, that's the end of volumes of revolution. And we're always going to make our choice not on which one we like better so much, but what's the best way to make the rectangle. Once we know the way to make the rectangle, then we know we either have to do discs or washers if it's perpendicular, or we have to do shells if it's parallel. So we've kind of finished all our volumes now as far as applications of the integration. Now we can get into a lot of new exciting things starting tomorrow. So see you then, I hope.